Right at the brink of Niagara Falls, Ontario, a
High above the frozen falls, a view you could only get by sending up a drone. Once again, here's Dylan Dreyer.
The USGS raised a red alert after recently analyzed satellite imagery showed something no one expected: a web of developing cracks stretching from the base of Niagara Falls toward the Appalachian fault systems. This sudden discovery thrusts one of the most famous landmarks on Earth into a spotlight not for its beauty or tourism appeal, but for its potential role in a larger geologic puzzle that could reshape how scientists understand stability across the eastern United States. The concern was not born of a single fracture, but of an alignment that suggests tectonic stress may be redistributing across zones that were thought to be largely dormant. Before we start, smash the like and subscribe buttons for more updates. At the heart of this revelation lies the constant, if often invisible, tension that exists beneath the crust of North America. Niagara Falls has long been seen as a powerful erosional feature, with water carving relentlessly through layers of dolostone and shale. For centuries, scientists and engineers tracked the fall's natural recession, but cracks connecting its underlying strata to deep fault lines were never considered part of the risk profile. The satellite data, however, changes that perception dramatically. High-resolution imaging and ground-penetrating sensors revealed that fractures are not isolated to the falls themselves, but are aligning in a southeastern trajectory. That path connects with the Appalachian system, which cuts like a scar through the eastern seaboard, extending from Alabama up through New England. The Appalachian Mountains are remnants of ancient collisions, mountain building events that date back hundreds of millions of years. Their faults are relics, but not entirely inactive. Minor tremors occasionally ripple through the region, rarely garnering more than local news coverage. Yet if cracks at Niagara are indeed channeling strain toward these fault zones, then what was considered an old, quiet system might in fact be primed for more activity than previously assumed. The Red Alert designation underscores the urgency. It is a call to scientific communities and policymakers alike that something profound is unfolding beneath the surface. What makes this situation compelling is the scale of the landscape involved. Niagara Falls sits at the boundary of two Great Lakes, channeling the mighty Niagara River from Lake Erie into Lake Ontario. Billions of gallons of water plunge daily over its precipice, and the erosive force is unmatched in the region. This immense hydraulic action has always reshaped local geology, but the new fractures extend far beyond what water alone could be blamed for. That suggests tectonic forces are amplifying the process, using the falls as a release valve. In essence, the energy of ancient bedrock is finding expression in one of the world's most visited natural wonders. Geologists examining the satellite evidence note patterns of stress marks running in parallel lines, each fracture widening in incremental progression. When cross-referenced with seismic monitoring stations scattered throughout the region, subtle upticks in ground vibrations became apparent. These tremors are not yet strong enough to be felt by residents, but instruments show their persistence. The cracks appear to be forming a geologic corridor, one that may be knitting together the fall's bedrock with larger fault dynamics across Appalachia. The fear is not necessarily immediate catastrophe, but rather a recognition that the eastern United States may not be as geologically stable as once thought. Niagara Falls is more than a tourist attraction. It is a vital hydrological engine. The falls support hydroelectric plants that generate massive amounts of power for both the United States and Canada. If the fractures compromise stability at the site, engineers could be faced with unforeseen challenges to energy production. Infrastructure built around the assumption of steady ground may have to be re-evaluated in light of the USGS findings. The red alert is not meant to signal impending collapse, but it does mark a shift in risk perception, especially in sectors that depend on the falls as a consistent natural resource. Beyond energy, there is the ecological dimension. The Niagara River and surrounding watershed are home to delicate ecosystems that thrive on predictable water flow and stable terrain. Any alteration in the geology could affect erosion rates, sediment dispersal, and even the habitats of fish and bird species that rely on the fall's unique conditions. A fracture system linking into deeper fault lines could subtly or dramatically alter how the river carves its path. Over decades, this could mean shifts in the shape of the falls themselves, something scientists always anticipated, but perhaps on a much faster and more erratic timeline. The cultural implications are equally striking. Niagara Falls has long been a symbol of raw natural power, drawing millions annually to marvel at its beauty. Its image is etched into art, literature, and collective imagination as a permanent monument to nature's might. But permanence is now in question. The idea that this icon might be linked to subterranean instability transforms it into a reminder that nothing in geology is static. Visitors gazing at its mist and roar may now be unwitting witnesses to the early stages of a tectonic drama that spans hundreds of miles. Scientists at the USGS have emphasized that the red alert is precautionary. It signals elevated monitoring, increased data collection, and collaboration between institutions. Satellites will continue to scan the area, while drones and ground teams work to confirm the fracture's extent. Seismometers across the Appalachian corridor are being recalibrated to catch the smallest of tremors. This network of instruments, when combined, can reveal whether stress is building toward a significant seismic event. The challenge lies in the timescale. Geological processes can unfold over years, centuries, or even longer, making predictions difficult. Yet the cracks themselves are real, and their alignment with known fault structures raises enough concern to demand attention. One of the more intriguing aspects is how this finding challenges assumptions about Eastern North America's geologic quietude. For decades, the West Coast has dominated earthquake preparedness efforts. California's San Andreas Fault is synonymous with seismic risk, and resources have been poured into monitoring it. The East, by contrast, has often been considered relatively immune to such concerns. The discovery at Niagara suggests that fault systems once thought dormant may still possess latent energy, waiting for the right conditions to express themselves. If Niagara is part of a chain reaction, then the East may require a fundamental reassessment of hazard planning. Local communities near Niagara Falls are also caught in the orbit of this discovery. The city of Niagara Falls, straddling the US and Canadian sides, is deeply dependent on tourism. The very notion that cracks are connecting the falls to larger fault lines could reshape how visitors perceive the destination. While some might be drawn by curiosity, others may be wary of potential instability. This dynamic underscores how geology does not just shape landscapes, but also economies and cultural identities. Researchers are particularly fascinated by how satellite technology made this revelation possible. Modern imaging systems are capable of detecting ground shifts at millimeter scales, something invisible to the human eye. These cracks may have gone unnoticed for years, hidden beneath vegetation, infrastructure, or the sheer scale of the landscape. But satellites peering from orbit captured their progression, giving scientists a powerful new tool to anticipate change. This represents a fusion of space-age technology with age-old geologic inquiry, where every pixel of an image can alter how humanity understands the Earth beneath its feet. The Appalachian fault lines themselves carry a storied history. Formed during the assembly of the supercontinent Pangaea, they are remnants of continental collisions that pushed ancient seafloors skyward into mountains. Though eroded over time, their fractures remain as pathways of weakness in the crust. For Niagara's cracks to align with these pathways suggests that the past is not as buried as once imagined. The ghost of Pangaea may still haunt North America, with stress redistributing along lines etched hundreds of millions of years ago. The implications reach beyond geology alone. Civil engineering, disaster preparedness, urban planning, and environmental policy may all need to integrate this new data. Bridges, power plants, and cities across the Appalachian corridor sit atop these fault zones. If subtle activity is returning, then safety codes and contingency plans must evolve. A red alert from the USGS is not issued lightly, and its weight lies in the acknowledgement that cracks at Niagara are not local oddities but part of a continental-scale conversation. Energy infrastructure presents one of the most immediate concerns. Hydroelectric stations at Niagara Falls are masterpieces of engineering, harnessing gravity and flow to produce power, but their efficiency relies on stability. If fractures alter water distribution or undercut bedrock, the entire system could face vulnerabilities. Engineers will now have to incorporate geological monitoring into operations, ensuring that energy supply remains uninterrupted even if the land itself begins to shift. Environmentalists see another layer of urgency. The Niagara region is a protected area in many respects, with parks, reserves, and conservation projects centered on its unique ecology. Cracks that connect to deeper fault systems might introduce unpredictable water table fluctuations, altering wetlands or river tributaries. Species that have adapted to the fall's environment over millennia may suddenly face challenges as their habitats transform in response to geological shifts. Monitoring ecological responses will be as critical as measuring the fractures themselves. For the millions who live along the Appalachian corridor, the news resonates in quieter, more personal ways. Many towns and cities dot the landscape, built on the presumption that their ground is stable. Families, businesses, and communities do not often consider the deep history beneath their feet. But as USGS reports spread, people are beginning to understand that ancient mountains may still hold restless energy. The falls, long celebrated as a symbol of permanence, now serve as a reminder that Earth's systems are always in motion. The broader scientific community is eager to learn from this case. Cracks at Niagara may become a textbook example of how stress redistributes across old fault systems. The discovery highlights the importance of constant observation, even in regions assumed safe. Satellite surveillance, seismic instruments, and geologic mapping together form a triad of modern science that can illuminate changes invisible to everyday life. By studying Niagara's cracks, scientists may develop better models for predicting stress transfer in other supposedly quiet regions across the globe. This revelation also redefines humanity's relationship with natural landmarks. People have long approached Niagara Falls with awe, taking it as an emblem of unchanging grandeur. The new fractures suggest that even the most iconic places are transient in the face of Earth's forces. This understanding does not diminish the fall's majesty, but enriches it, framing it as part of an evolving planet whose landscapes are never finished. The cracks linking Niagara to the Appalachian system weave the falls into a story that is not just local or national, but continental. In the months and years ahead, the world will watch closely as monitoring continues. Every satellite pass, every seismic reading, and every geologic survey will add new pieces to the puzzle. The Red Alert has focused global attention on Niagara not as a tourist wonder, but as a critical site in Earth science. For scientists, it is an opportunity to study the deep dynamics of tectonic processes in real time. For communities, it is a reminder of vulnerability and resilience. For everyone else, it is proof that the ground beneath us is never as quiet as it seems. And so Niagara Falls, a place of timeless wonder, now becomes a place of urgent study. Its cracks are not just fissures in stone, but openings into questions about stability, history, and the future of a vast region. As they connect to Appalachian fault lines, they remind us that Earth is an active participant in its own story, shifting and reshaping even the landmarks we believe to be eternal. In the spray and roar of the falls, there is now another sound, quieter, deeper, but no less powerful. The whisper of tectonic forces stirring beneath the surface. The cracks discovered near Niagara Falls and their suggested link to the Appalachian fault lines represent more than a geological curiosity. They open up a wide set of inquiries into how humans have underestimated the eastern half of North America for centuries. Much of the continent's popular image of seismic risk has been dominated by the San Andreas, the Cascadia subduction zone, or Alaska's tectonic volatility. But the East, though often silent, has its own seismic story that periodically resurfaces in subtle tremors or dramatic quakes, like the one that shook Virginia in 2011. The new fractures at Niagara breathe fresh urgency into studying these less appreciated hazards. The historical record is filled with instances of eastern seismic unrest, though rarely do they capture headlines. The Charleston earthquake of 1886 remains one of the strongest recorded on the East Coast, toppling buildings and killing dozens. Its scars still appear in South Carolina architecture, where earthquake bolts crisscross historic structures as reminders of vulnerability. The fact that such an event occurred far from the seismic hotbeds of the West was once thought an anomaly, but the presence of faulted bedrock beneath the Appalachians suggests it was never an isolated occurrence. The cracks at Niagara could be the opening lines of another chapter in this long, understated history of Eastern seismicity. The East presents a unique challenge because its geology differs from the fractured, constantly moving plates of the Pacific Rim. The crust in this region is older, thicker, and more rigid. When stress accumulates and eventually releases, seismic waves travel farther than in the fractured crust of the West. A quake in Virginia, for instance, was felt as far north as Canada and as far west as the Midwest. This makes the new fractures all the more concerning. If strain is truly redistributing from Niagara toward the Appalachian system, then even a moderate quake could have far-reaching effects, impacting cities and towns hundreds of miles away. The alignment of the cracks suggests stress pathways that extend beneath landscapes dotted with major population centers. Washington, D.C., Philadelphia, Pittsburgh, Atlanta, and other eastern cities lie along the Appalachian corridor. These cities were not built with seismic resilience as a central concern. Their infrastructure, bridges, high-rises, transit systems, has largely focused on resisting weather, flooding, or age, not tectonic jolts. If the cracks at Niagara are indicators of deeper structural weakness, then planners may need to rethink how resilient the East's built environment truly is. The discovery also forces attention back to hydrogeology, the interaction between water and rock. Water has always been a powerful shaper of land, but in fault zones it can act as both a lubricant and a destabilizer. Niagara, with its immense volumes pouring over daily, could be accelerating stress migration by allowing water to seep into microfractures, widening them and reducing the friction that holds rock masses in place. If water continues to infiltrate the cracks identified by satellites, then fault reactivation becomes more plausible. The presence of such a massive hydrological engine at the edge of a seismic corridor gives scientists a natural laboratory, though one with potentially dangerous implications. From a scientific standpoint, the Niagara fractures demand an interdisciplinary response. Seismologists alone cannot interpret all the dynamics. Hydrologists, structural engineers, ecologists, urban planners, and even sociologists must weigh in. Each field brings different lenses, whether analyzing water's role in fault lubrication, predicting how buildings will withstand shocks, or assessing how communities will adapt psychologically to a new perception of risk. What begins as a set of cracks becomes a crossroads of disciplines, each seeking to understand how a continental system is shifting in real time. Remote sensing will likely dominate the next phase of investigation. Satellites orbiting Earth can revisit the Niagara corridor every few days, comparing snapshots to detect minute changes. These tools employ interferometric synthetic aperture radar (INSAR), a technique capable of detecting ground deformations smaller than a centimeter. By layering hundreds of such scans, scientists can build time-lapse models of how the fractures grow, shift, or pause. Already, INSAR has revolutionized volcano monitoring, glacier dynamics, and earthquake studies. Applying it at Niagara opens an unprecedented chance to watch stress redistribution across a fault system in near real time. At the same time, ground-based instruments must fill in the gaps. Borehole sensors drilled near the falls could detect subtle shifts in pressure, temperature, and water chemistry. These changes often precede seismic events, providing valuable clues. GPS stations anchored in bedrock may also reveal slow-motion movements of the crust, impossible to detect without precision technology. Together, these instruments create a layered monitoring network, space above, sensors within, and instruments across the land, all converging on the mystery of the Niagara fractures. Yet the question remains, why now? For centuries, Niagara has thundered on. Its bedrock gradually eroded but never dramatically linked to deep tectonic instability. One theory suggests that climate change may be influencing subterranean dynamics. Warmer temperatures have altered precipitation cycles across the Great Lakes, swelling and receding water volumes more dramatically than in the past. These fluctuations place additional stress on the rock below. Heavy rains saturate soils and increase hydrostatic pressure, while droughts reduce stabilizing water weights. Such cycles may be subtly agitating faults that have long been dormant, coaxing them toward activity. The Appalachian corridor itself is a reminder that ancient scars never fully heal. During the assembly of supercontinents, faults acted as highways of stress, guiding energy across vast terrains. Even as mountains eroded and continents shifted, these pathways remained weaknesses in the crust. Modern stress, whether from glacial rebound, water loading, or regional plate interactions, may be reawakening these ancient channels. Niagara's cracks could be the clearest surface manifestation yet of this reawakening, forcing a reappraisal of what was thought to be a geologically quiet region. For communities, the implications extend into the realm of preparedness. Earthquake drills, evacuation plans, and reinforced infrastructure are familiar to Californians and Alaskans, but foreign to many in the East. The red alert serves as a wake-up call. Even if the cracks do not herald imminent catastrophe, they remind policymakers that complacency is dangerous. Preparedness is not about predicting the exact moment of disaster, but about ensuring resilience when surprises occur. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on these cracks near Niagara Falls? We want to hear from you. Thank you for watching, and see you next time.